The goal of this video is to use what we know about the recognition theorem for direct products to prove a big piece of the primary decomposition theorem. Remember, this is this theorem that's equivalent to the fundamental theorem of finitely generated abelian groups, specialized to the case of your group actually being a finite abelian group. So remember, we divided the primary decomposition theorem into parts. And we already know that every finite abelian group is isomorphic to a direct product of its CELO subgroups. So that's something that we proved when we were first talking about consequences of CELO's theorem. So our goal is going to be to prove theorem 5 part 2 in section 5.2 of Dummett and Foote, this piece of the primary decomposition theorem, which says we're just going to think about the case where G is a finite abelian group of prime power order. So a group of order p to the n, where n is at least 1. So a non-trivial finite p group, finite abelian p group. What we want to show is that G can be written as a direct product of prime power order cyclic groups. So G is isomorphic to z mod p to the beta 1z cross z mod p to the beta 2z cross z mod p to the beta tz, where these beta i's are in non-increasing order. They're all at least 1, so these groups are non-trivial. And okay, if these are isomorphic and G has order p to the n, then the order of the group on the right-hand side better also be p to the n, which just is the same as saying that beta 1 plus beta t is n. So what's really going on here? This thing about ordering them and the size, there's nothing really to do, right? If we had some other ordering where maybe these weren't non-increasing, we could just rearrange the factors and we would get an isomorphic group. So what is our real goal? Our real goal is to say, let's start with a finite abelian p group of order p to the n. We can write this group as, or this group is isomorphic to a direct product of prime power order cyclic subgroups, cyclic groups. Okay, so the big thing that goes into this argument is a lemma. And this lemma says, suppose that G is an element of your group G that has maximal order. What is this group G? G is a finite abelian group of order p to the n. So suppose that little g is an element in this finite abelian group of order p to the n that has maximal order. Then the group is isomorphic to the cyclic subgroup generated by little g cross h for some subgroup h of g, where the intersection of h and the cyclic subgroup generated by g is the identity, is the trivial subgroup. Okay, let's assume that this lemma is true for now. And now let's prove the theorem. So the big idea here is that we're going to argue by induction on the order of G. So what's the base case? Well, n is at least 1. If G is order p to the 1, G is order p, and G is isomorphic to z mod pz, end of story, right? So that takes care of this case. We would have beta 1 equals 1 and t equals 1. Like, that's it. Okay, so when n equals 1, there's pretty much nothing to prove because we already know that every group of order p is cyclic. All right, so now let's suppose that the order of G is p to the n, where n is bigger than 1. And we're going to do the same thing in the proof of the theorem that we do in the lemma, which is we're going to zero in on some element little g in the group that has maximal order. Two cases. If the cyclic subgroup generated by this little g is our whole group, then we're done. Because now we've seen that our group is cyclic, so it's isomorphic to a cyclic group. Like, there's nothing else to do. So if not, then we're going to apply this lemma. So we have G, this group of order p to the n. We have an element, little g, of maximal order. And G is not isomorphic. This group G is not the cyclic is not cyclic, the cyclic subgroup generated by G. So by the lemma, what does that mean? That G is isomorphic to the cyclic subgroup generated by G cross H for some subgroup H of G, where the intersection of H and this cyclic subgroup generated by little g is trivial. So in this case, G is isomorphic to Z mod order of G, Z, cross H. Since G is a finite abelian group of order p to the n, the order of G is some prime power. It's p to the beta 1 Z for some beta 1. And what do we know about H? It's a subgroup, and it has order p to the m, where m is less than n. We know it's not the trivial subgroup because we know that G is not cyclic, right? G is not equal to the cyclic subgroup generated by G. So the order of H, it's p to the m for some m that's at least 1 but is less than n. So now we apply the induction hypothesis. And what does that say? That says that H is isomorphic to a direct product Z mod p to the something Z cross Z mod p to the something else Z cross Z mod p to the something else Z. So H is isomorphic to a direct product of cyclic groups of prime power order, and the cyclic subgroup generated by G is a cyclic group of prime power order. So we have seen how to write G as, or we've seen that G is isomorphic to a direct product of cyclic groups of prime power order, and we're done. So what is the recap? Is if you want to remember how this proof works, there are two big things to remember. One is that the proof goes by induction on the order of G, and two, you have to remember this lemma. If you remember this lemma, that you take an element inside your group of maximal order and you write G as isomorphic to cyclic subgroup generated by that element cross some other subgroup H, then that will help you to remember that when you're proving the theorem assuming the lemma, the main idea is the same. You take an element of maximal order and you apply the induction hypothesis. So I'm going to pause and erase, and then I will talk about the proof of this critical lemma. Let's begin our discussion of the proof of this critical lemma. So what are we trying to prove? Let G be a finite abelian group of order p to the n, and let little g be an element in your group of maximal order. Then the group G is isomorphic to the cyclic subgroup generated by this element little g cross H for some subgroup H of G, where the intersection of the cyclic subgroup generated by little g and H is the trivial subgroup. All right, we're going to prove this by induction on n, just like the proof of the theorem assuming the lemma. So if the order of G is p to the 1, then an element of maximal order has order p. So in that case, G is isomorphic to a cyclic subgroup generated by any non-identity element cross the trivial subgroup. And we're done. So what we'll do is suppose the order is p to the n, and that the statement holds for all finite abelian groups of order p to the k, where k is any positive integer less than n. Let little g be an element in your group of maximal order. So an idea we've already seen a couple of times. Say that this order is p to the m. Okay, what does that tell us? If this is the maximal order of any element, then you take any element in the group, you raise it to the p to the m power, and you get the identity. So if this is the maximal order, then every element has order p to the something. So if p to the m is the biggest one of those somethings, the order of every element in G divides p to the m. So we'll use this later. So here's the big idea. The first big idea here is we're going to pick an element H in our group G to not be in the cyclic subgroup generated by little g that has minimal order in the group G. Okay, so this idea is not so obvious that this is the right thing to do, but we'll see that it works nicely. And And this is one of the big things to remember for this argument. Okay, first, what if there is no such H? Well, that would mean that every H in your group is in the cyclic subgroup generated by G. So the cyclic subgroup generated by G is the group G. And we're done. There's nothing else to do because you can say that G is isomorphic to the cyclic subgroup generated by G cross the trivial subgroup, and we're done. So now what are we going to do? We're going to let H be the cyclic subgroup generated by this little h, the element that's not in this subgroup generated by G that has minimal order. And what do we want to do with this subgroup? We'll show that the intersection of the cyclic subgroup generated by G and the subgroup H is the trivial subgroup. And the way that we're going to show that that intersection is trivial is by showing that the order of this group H is exactly P. So that, what's another way to say that? H in G is an element not in the cyclic subgroup with minimal order. We're saying that there is such an element where that order is P. Right? So that's the smallest that the order of a non-identity element could be. So why is this enough to say that the intersection of the cyclic subgroup in H is 1? Well, by Lagrange's theorem, the intersection of these two subgroups is a subgroup of each one. So if the order of H is P, then the order of this intersection is something that divides P. And because H is not contained in this cyclic subgroup, it's strictly smaller than H. So it's a proper divisor of P. And the only one of those is 1. Okay, so I'm going to pause and erase and then tell you not the proof of this statement right here, but tell you, assuming that this statement is true, how is the rest of the argument going to go? Let's continue with the proof of this important lemma. So what is our setup? Little g is an element in our group of maximal order before we decided to call that order p to the m, and the order of the group is p to the n. We took little h to be an element that's not in the cyclic subgroup generated by this little g that has minimal order. We let capital H be the cyclic subgroup generated by little h. And then we claimed that the order of this group H is P, and saw that that showed that the intersection of the cyclic subgroup generated by G and H is the trivial subgroup. Okay, we're going to assume that for now. We'll prove that in a few minutes. I'm going to make another claim that we're going to use. So star here, star star, claim 2, says the order of the left coset of H containing little g in G mod H is the same as the order of little g in capital G in the group. So remember, this is p to the m. So I claim that the order of this element in this quotient group is still p to the m. What does that get us? Well, the order of this element of a quotient group, the left coset of H containing x, that's at most the order of x in G, right? Because the order of x in G is the smallest power you have to take to get to the identity. And the order of this coset is the smallest power of x you have to take so that you land back in H. It doesn't have to be the identity, but it has to be in H. So this number is at most this number. So what does that mean? So if the order here is p to the m, that means that that order is maximal in this quotient group, because there's no way for the quotient group to have an element whose order is bigger than the order of any element in the group G. Okay, so now assuming these two claims, what are we going to do? Well, what's the order of the quotient group? It's p to the n minus 1, right? Because G has order p to the n, and H has order p. That's from claim star. So by induction, we've supposed that the lemma is true for this finite abelian group of order p to the n minus 1. So G mod H is isomorphic to this cyclic subgroup generated by the left coset of H containing G, this element of maximal order in the quotient, cross some other subgroup, Q of the quotients. And we know that the intersection of the cyclic subgroup with Q is going to be the trivial subgroup. Okay, but what do we know about Q? This is some subgroup of a quotient group. Well, what is the thing that tells us about subgroups of quotient groups is the lattice isomorphism theorem. This says that there exists a subgroup K of G containing H as a subgroup. So there exists a subgroup K of G so that H is a subgroup of K and Q is equal to K mod H. Remember, we're in an abelian group, so everything is automatically normal and we don't have to worry about these quotients being defined. Okay, so what does this say? Where are we? So G mod H is isomorphic to this cyclic subgroup cross K mod H. So I'm going to make one other claim that we're going to prove after we pause and erase, and I'll call it star, star, star. So our last claim is going to be that given this setup, the intersection of the cyclic subgroup generated by little g and K, this subgroup, is the trivial subgroup. Okay, now we're going to use that to say something about the internal direct product of the cyclic subgroup generated by G and K. Well, by star, 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 we know that the intersection has size 1. So what's the order of this internal direct product of this product set? Is just the product of the orders. Usually you get the product of the orders divided by the size of the intersection. But if this intersection has size 1, you just get the product of the orders. And what is that product? Well, G has order p to the m. What's the order of K? Well, to figure that out, let's look up here. The left-hand side has order p to the n minus 1. GH has order p to the m. So K mod H has order, okay, let's do some arithmetic. So it's p to the n minus 1 minus m. Or p to the n minus m minus 1. So then what's the order of K? Is p to the n minus m. So what's the order of this product? It's p to the m times p to the n minus m. It's p to the n. So it has to be everything in G. So G is equal to this internal direct product of the cyclic subgroup generated by little g and K. These subgroups are both clearly normal because we're in an abelian group. And their intersection is the trivial subgroup. So by the recognition theorem for direct products, G is isomorphic to the cyclic subgroup generated by this little g cross this subgroup K that we got out of the induction hypothesis applied to G mod H plus the lattice isomorphism theorem. Okay, so this is the thing that we wanted to prove. So what do we have to do to prove this theorem? To prove this lemma, I guess. We have to justify this claim star, star, star. And this is straightforward. I'll do this at the top of the next board. And then we have to justify this claim about the order of the left coset of H containing little g versus the order of little g. That's also pretty straightforward. And then we have to justify this claim that the order of H is P, that there exists an element, little h, not in the cyclic subgroup generated by G, of order P. Okay, so I'll pause and erase, and then we'll just do those 1, 2, 3. We have 3 claims left to prove, and we're going to do them in backwards order. So first, at the end of the proof, we claimed that the cyclic subgroup generated by G intersect this subgroup K that came out of the induction hypothesis applied to G mod H plus the lattice isomorphism theorem is the trivial subgroup. So we'll prove this by asking, what does it mean for something to be in this intersection? So if B is an element that's in the intersection of the cyclic subgroup generated by G and K, then what does that mean when you work in the quotient by H? Well, that means that the left coset of H containing B is in the cyclic subgroup generated by GH intersect K mod H. And by induction, what is this intersection? This is the trivial subgroup. This is something that came out of applying the induction hypothesis to the group G mod H. So what does that mean? Well, if BH is equal to the trivial element in this quotient G mod H, that means that B is in H. So now we know that B is in the cyclic subgroup generated by G, and not just K, but the smaller group H. And by star, the whole point of star is to prove that the cyclic subgroup generated by G intersects H is the trivial subgroup. So that means that B is the trivial element. So what does that mean? The only things in the intersection of the cyclic subgroup generated by G and K is the trivial subgroup. Okay, what about star star? This second claim was about the order of the left coset of H containing little g in G mod H is equal to the order of little g in G. So how are we going to prove this? We're going to suppose that the order was smaller than p to the m, the order of G, and we're going to see that there's a problem. So if the order of this coset is less than the order of G, less than p to the m, then what does that mean? Well, let's take this coset and raise it to the p to the m minus first power. Definitely the order is some power of p, and if it's less than p to the m, then it's at most p to the m minus 1. So if you take gh and raise it to the p to the m minus 1, you have to get the left coset of H containing 1. You have to just get the identity in this quotient group. But what is that? That is the left coset of H containing g to the p to the m minus 1. So, okay, that element is definitely in the cyclic subgroup generated by G, and it's also now in H. But star is showing that the cyclic subgroup generated by G intersect H is the trivial subgroup. So that means that G to the p to the m minus 1 is the identity. And what does that mean? That means the order of G is not actually p to the m. It's less than or equal to p to the m minus 1. And this is a contradiction. So this proves star star. And the only thing that we have left to prove now is that with our definition of the subgroup H, how we constructed it, that the intersection of the cyclic subgroup generated by G and H is the identity, which remember we said we're going to prove by showing that the order of H is P. So I'll pause and erase, and then we'll do this final piece of the proof. Let's prove the last piece of this lemma. So all we have to show is this claim star. And the way we're going to do it is to show that there is some element x in G of order P where x is not in the cyclic subgroup generated by little g. So why is that enough? So we assumed that little h in G was an element such that H was not in the cyclic subgroup generated by G with minimal order. So if we can show that there's some element that's not in this cyclic subgroup that has order P, then this H must have order P by this minimality assumption. Okay, so what do we know about the order of an element in a finite abelian P group? The order is some power of P. So taking what we know about what happens, you have the order of some element and then you raise it to a power and ask for the order. We know that the order of H to the P is the order of H divided by P. So in particular, that's smaller than the order of H. And since we assumed that H was an element of minimal order, not in the cyclic subgroup generated by little g, that means that H to the P is in this cyclic subgroup. So what does that mean? H to the P is G to the R for some integer R. Okay, what can we say about R? It must be true that P divides R, Because otherwise, so the order of G is some power of P. If this is not true, then R is relatively prime to the order. And the order of G to the R is the same as the order of G. So where does this come from? I mean, this and also this. If you don't remember these kinds of facts, you can look at proposition 5.2 in section 2.3 of Dummett and Foote on cyclic subgroups. So what's wrong if the order of G to the R is equal to the order of G? Well, then the order of H to the P is the same as the order of G. And the order of H is even bigger than the order of G. And that's not possible because we assumed that G had maximal order in this group. Okay, so what do we know? We know that P divides R. So R is P times S for some integer S. So then what is H to the P? It's G to the R, it's G to the P times S. So what do we do all this for? Let's let A be equal to G to the minus S times H. Okay. This seems to come out of nowhere, but we'll see that it works. What do we need to check? We need to check that A is not in the cyclic subgroup generated by G, and that A is an element of order P. So A is not in the cyclic subgroup generated by G. If it were, then, okay, if you multiply A by a power of G, by G to the S, then you get H. So if A is in the cyclic subgroup generated by G, then so is H. But we assumed that H was not in this cyclic subgroup. So okay, A cannot be in this cyclic subgroup. A to the P, what is that? Well, it's G to the minus SP times H to the P. But that's G to the minus R times G to the R, which is the identity. So, okay, so what do we need? That means that A is an element where you raise it to the P power and you get the identity. That means either it has order P or it's already the identity. But if it's already the identity, then H equals G to the S. And that's not possible because we suppose that H was not in the cyclic subgroup generated by G. So what does that mean? That means A is our element in G that has order P and is not in the cyclic subgroup generated by G. That is the element that we were searching for in this proof. Okay, so let me say, I think that this is probably the hardest proof that we have done so far in this course. Not so much because it's difficult to verify line by line that all the statements are true, but the structure of the argument is a little complicated. In particular, what was the hardest thing that we did here is we had to show you take some element of maximal order. Then you take some element of not in the cyclic subgroup generated by that maximal order element that has minimal order. And you have to show that that minimal order is P. And the way that you do it is like a little bit clever and involves some facts about the orders of powers of elements. And it's not like really straightforward. So this, I think, is the trickiest part of the proof to remember. But even once you remember this claim, there's still the other pieces that go into the proof of this lemma. So I think this is an argument that's good to study, but this is not the kind of thing that you would see on an exam in this course.